Hey everyone, and welcome to week 2 of module 1. So we've been talking a lot about oxygen transport and CO2 transport and different circulatory mechanisms, but I'd like to go over some equations that are involved in oxygen transport. The reason I like to go over these things is because, once again, you can see the parts of the whole. So you can see how oxygen is transported, how oxygen is measured in the arterial blood, venous blood, and things like that. So sometimes it can give a clearer picture of what's going on. Also, it can enable you to be more precise in your communication, giving specific values to certain situations, or even just understand the carrier of patient better. What I like to do is I do use equations quite often, the ones I'm going to show you today, in my care of ECMO patients. It's very helpful because you have all the numbers. You might as well make use of them and really understand what you're looking at. So we're going to start off with, this is essentially a review. These are equations that you probably have learned before, but maybe not have used in quite some time. So this is essentially a review and a presentation of these things. One other thing, you will see these equations and calculations in the ACCS credentialing exam. You'll also see them on my exam, so I think it's helpful to go over these things again. All right, so we're going to start with our first one, and that's going to be the CaO2. Okay, so the CaO2 is pretty much a measurement of the arterial blood's oxygen carrying capacity. So it is defined by 1.34, which is the number of mLs that can dissolve in 1 gram of hemoglobin. Okay, so then we have a hemoglobin concentration in grams per deciliter, and then we multiply that by our SaO2, and that's as a percentage, so point whatever, so let's say 0.95, for example. All right, and then we're going to add 0.003, which is the solubility coefficient for oxygen in the plasma, dissolved in the plasma. Okay, so that is times the PaO2. So the CaO2 is 1.34 times the hemoglobin concentration times the SaO2 plus the oxygen solubility coefficient times the PaO2. All right, so our normal values for this are about, we're just going to say 20 volume percent. All right, and now volume percent also means ml per deciliter. All right, and the reason I say that is because if you're converting units or maybe canceling things out when you're doing your math, which you probably will never have to do, but it's just good to know, and also just for some perspective, that volume percent is actually mLs per deciliter. It's interchangeable. You can write it either way. I just like writing volume percent because that's what I'm used to doing. All right, so I think the best way to illustrate the different aspects of this equation briefly is to just do a quick little scenario. And by scenario, I mean just abnormal lab values. So let's say we have a sick patient. Okay. All right, so let's calculate their CaO2. So we're going to take the 1.34. That's going to show up. .34. And let's say this patient has a hemoglobin of 7, which is low, right? And then their SaO2 is 0.93. And we'll add the solubility coefficient times the PaO2, which is, we'll say it's 71. All right, so this patient has a CaO2 of 9 volume percent. All right, so in the ICU, you're going to see this quite often. So essentially, this is going to be your new normal in sick people, low hemoglobin situations or anything like that. One thing to note is that you'll often read in literature that this equation states the importance of hemoglobin for the oxygen carrying capacity of blood. As you can see here, 7 is the hemoglobin. If we were to increase that to, let's say, a normal value like 14, this number would essentially double. Okay, so that would that states the importance of hemoglobin as far as transporting oxygen. But in low hemoglobin states, let's say you're giving this person 100% oxygen, this side of the equation that I'm boxing out right now actually has more of an effect in that specific situation. So just be aware of that. Another thing, as far as calculations of this equation go, and this will go for another equation that I'm about to go over, I'm going to put an X here, this side versus this side of the equation. If you're taking a test and you want to be quick, just calculate this side of the equation, all right? So the ACCS or whatever it is, it's faster and you'll get just as good of an answer for a test. So you don't necessarily have to calculate this side because it's a negligible amount, as you can see how low that coefficient is or how small, okay? And how small of a percentage of the PaO2 is going to contribute there. So that's that. The sister calculation for the CaO2 will be the CvO2. We're not going to go into too much detail because it's essentially the same thing, just with venous parameters. So 1.34 times hemoglobin concentration times SvO2 plus 0.003 times PvO2. Okay? The normal value for CvO2 is about 15 volume percent. All right? So what that means is that the difference between the CaO2 and CvO2 normally is 5 volume percent. Makes sense, right? All right, so you might see that as well in some of your tests. All right. So the next thing I want to go over is the DO2, which is a very important measurement parameter for the delivery of oxygen. So now the CaO2 only tells us the carrying capacity. All right, C carry. The DO2, on the other hand, will tell us how much is delivered to the tissues. Okay, D delivered, and that's what that stands for anyway. So the DO2 equals, so we have to know how much oxygen is being carried out of the blood, or in the blood to the tissues. So we're going to take our CaO2, right, because that's our carrying capacity of oxygen in our arterial blood. We're going to multiply that by our cardiac output. So our heart has to pump the blood, doesn't it? And then we're going to multiply that by 10. And this is just a factor to change the units. As you remember, this was mLs per deciliter, and this is ml per minute, okay? So what you're going to get is your delivery of O2, which is about 900 to 1100 mLs per minute, okay? 900 to 1100 mLs per minute. So let's do a quick scenario with the DO2 here. So let's say we have our sick patient again. So the one we calculate up here with the hemoglobin of 7. So that patient's CaO2 was 9 volume percent. Remember that? So let's just do equals the DO2 in our equation. So the sad face again is 9 volume percent times, let's say 4.5. So it's a relatively lower end of cardiac output. So 4.5 liters per minute times 10. And that will give us a DO2 of 405 mLs per minute. Okay, so you can see that's significantly lower than the normal values for DO2. So this patient's low hemoglobin is contributing to a low oxygen arterial content as far as the carrying capacity goes, and is really affecting their delivery of oxygen with respect to their cardiac output. Okay, so with that said, our tissues need to extract the oxygen, and when you maybe have a low output state or a high metabolic state, your tissues are going to extract more oxygen and therefore produce more CO2. So to calculate that, we're going to use our O2 So oxygen extraction ratio, let me redo that. The oxygen extraction ratio is a unitless number, okay, because everything's going to cancel out here. And we use I'm going to use some different colors. So we're going to use the CaO2 minus the CvO2. All right. So let's send this out here. And then we're going to divide that by the CaO2. All right. So you get the difference between the CaO2 and the CvO2 as a percentage of the the total arterial oxygenation carrying capacity. This value normally is 0.2 to 0.3. Okay, and that's usually expressed as a percentage. So you can multiply that by 100, and you'll get 20 to 30%. Okay, so that's telling us that we usually extract 20 to 30% of our delivered oxygen to our tissues in a normal metabolic state. All right, so I'm not going to calculate a whole pathologic state for this equation because it's a little different. Usually bad means low means bad and high means good, right? But not in this case. A lot of times the extraction ratio will increase in sepsis. Any sort of higher metabolic state, low cardiac output potentially, and things like that. So usually in pathologic states, your O2 ER is going to increase. So just remember that, and you'll see how this works out in our next equation. And trust me, I'll stop the torture soon, in our VO2. Okay? So the VO2 can be calculated a few different ways. I think the easiest way, and with respect to this lecture as well, to calculate it is just to take the DO2, so the delivery of that oxygen to the tissues, DO2, and we're going to multiply that by our oxygen extraction ratio. And just like any of our other equations, we can do algebra if we're missing one of these values and determine the other one. So, for example, you can take if you want to divide out the O2 divide that out, VO2 divided by the O2 equals DO2. So you can kind of figure out things that way as well with this. So it's much more simplified, and I think that's a little beneficial. But anyway, so the VO2 is normally here is normally about 200 to 270 mLs per minute. Okay, that's maybe plus or minus 100 mLs or so, this way or the other. But for our purposes, that's what we're going to use today. So let me go back up to here, and it's going to be in yellow. You see up here at the top, the DO2, what was that, 900 to 1100 mLs per minute, so the delivery of oxygen to the tissues. And the oxygen used by the tissues in a normal metabolic state, not exercise, not fever or anything, is 200 to 270 mLs per minute. So you can see that more oxygen is delivered than what we need. And it's usually on a ratio of 4 to 1, usually. Okay, in a normal state, it's 4 to 1. So if you're taking care of a sick patient, and you can see that if you do these calculations and you can see that their DO2 to VO2 ratio is less than 4 to 1, you have a problem there. So if you have a 2 to 1 or a 1 to 1, you're getting into an issue there. So the body's taking up more oxygen, and at some point it becomes supply and demand. And we're going to call that supply and demand moment, the relationship between DO2 and VO2, as the critical DO2. Okay, so like I said, usually there's a buffer between the VO2 and DO2. At the critical DO2, we're extracting about 50%. And at that point, the relationship becomes supply and demand. So if you don't supply it, the demand's going to increase and you're going to go into anaerobic state, which happens quite often. So, all right, so that's the quick and easy of it. Just remember these normal values. Remember to kind of understand the previous equations because they all lead up into this final equation right here. I'm going to ask you to calculate some of these parameters in the examinations, but it's simply going to be plug and play. I feel like since these are open book, open note tests, you should have these written down somewhere so you can just refer to them quickly. All right. If you have any questions, feel free to email me, let me know, and I hope to see you guys next time. Thanks.